I've previously talked about the Ohm's law, which is a relation between voltage and current, and that led to the idea of a resistance, which tells us that, say, if I have a bigger resistance for the same voltage, I should have a smaller current. It gives us a measure of how much the light bulb or some other conductors as well resist the flow of current. Now, in this example, I've only looked at a very small voltage, like 1 or 2 volts. Okay, the typical light bulbs in our house that we use for lighting would operate at 1 or 200 volts, depending on which country you're at. So, at this for this little experiment that I described in the last video, with this very small voltage, I would expect that the light bulb would not have lit up. It would not be bright because it's just 1 or 2 volts. I really need to plug it into the mains with 100 or 200 volts before I'll see light. So it just means that in this experiment, there's actually no light. I'm just measuring some currents to see what the graph looks like, and it also means that the light bulb would probably be at room temperature. Okay, just a tiny bit of current flowing through it, 0.0 something of an ampere. So the light bulb wouldn't have heated up or lit up yet. So let's say in the beginning, the room temperature in this experiment was about 25 degrees Celsius, and that's the kind of graph that I get. Now, the thing with conductors that are made of metal, like maybe copper, or in this case for the light bulb, they are typically I'm referring to the type of filament light bulb. They're typically made of tungsten. Well, maybe typical might not be a very suitable word. It's just that many of the light bulbs that we can buy in the shops are made of tungsten. But today, of course, we have lots of different types of light bulbs. With maybe daylight lights, what's the energy saving light bulb, and all the like LED, light emitting diode light bulb. So it can be made of all sorts of materials with complicated principles and ways of operation. So, but for my example here, I'm just going to continue to talk about I'm mainly going to continue to talk about the tungsten filament light bulb, in which the light bulb is contains a very thin coil, or a very thin coil of metal wire made of tungsten metal. So that's the thing that the example that I'll continue to look at, maybe in this and the next video, as an example to learn about resistance and current flow. So for a metallic resistor, that's one way we can describe it, just a piece of metal that has resistance to the flow of electric current. It would normally obey Ohm's law, given by this equation, or you can think about it as a straight line graph when you plot current against voltage. It would normally have this behavior, this Ohm's law and straight line behavior, if we do this measurement at a fixed temperature. But if the temperature increases, the tendency is that the resistance would increase. The resistance would increase. And the reason for that is complicated. I'll just very briefly say that it's because when it gets hot, the atoms would have more kinetic energy. Like we learned in a much earlier video, there would be lots of movement in the atoms, and that would in some way disturb the flow of electrons through the filament, which is why it would then offer a bigger resistance to the current. So that should be enough description to keep us going for now. Let me now go back to this graph and continue with my description of an experiment to measure the current for different voltages and to see what the graph looks like. Only that this time, instead of just applying 1 or 2 volts, just very small voltages, I want to increase the voltage all the way to, say, 230 volts. For example, what might be the normal operating voltage of such a light bulb? So let me start by clearing this and drawing a new graph. That's my current axis. That's my voltage axis. So I have voltage and current. Now when we plot the graph, we should be careful about the units. So I'll put the units in brackets here, just to remind ourselves. Okay. So let me start with that very small voltage that we applied. Suppose that in the end, I want to take it all the way to maybe, I'll just say 200 volts. Let's say I want to take it all the way to 200 volts. But before that, let me just put in here, reproduce the previous measurement. When I use just 1 or 2 volts, let me just add those points here. So as right, when I applied 2 volts just now, I said that the current might be about 0.05 of an ampere. Okay, so that's the kind of and that's the kind of value, and we get a roughly straight line graph for this small voltage. So that was the kind of result that I got in my previous, that I described in my previous video. So I'm just going to shrink it down and draw it as a tiny graph at this corner, right? But this time I'm going to really increase the voltage all the way from 2 volts to 200 volts, right? Quite close to the 230 volts, for example, that we might want to operate this light bulb, right? Okay, and as I do this, I want to imagine measuring the current. As I increase the voltage, I want to measure the current, and I want to plot this graph as the current, as the voltage increases all the way to 200 volts. And for the light bulb that I described just now, if you remember, I was saying something like 230 volts, maybe 60 watts rating, a light bulb with this rating. Remember, this means that If I apply 240 volts, then it will be a 60 watt power given out as light and heat. It doesn't mean that if I apply a smaller voltage, I also get 60 watts. So that's just a rating. So using this light bulb, suppose that I'm going to just take a jump to 200 volts and see what happens. So I just change this to a very powerful battery or a special power supply that will give me 200 volts. And if I then measure the current, I would find maybe somewhere there a bigger current of say 0.0 no say of say 0.2. Okay, let's say I'll find a current of 0.2 amperes. So if I then plot the points of this, I would find maybe a point there. Okay. So in between, if I now go back to a smaller voltage and I say take it in steps of 10, maybe I do say 10 volts, 20 volts, 30 volts, 40 volts, and so on. And at each voltage, I measure the current. I would be able to plot a graph. Okay, I can plot a graph, and the graph will fill in the points. The graph will fill in the points of the graph. The points will fill in the graph that I want to measure. So I would most likely see something that looks like this. I would see a curve, right? I would not see a straight line anymore. Okay. Now, and the reason why I wouldn't see a straight line is that the resistance of the maybe I should explain this. I should think of this in another way. That if we actually carry out this experiment, we would find a graph that is at first quite straight, but as we increase the voltage to much higher value, you'll find that the graph curves, right? And then when we look at this graph, we need to try to understand why. We need to try to understand why this has happened. And one way to understand why is to say if we go back to the lower voltage, we would think that because the lower voltage part is a straight line, then by extension, we might expect that the graph would just go up in a straight line. Maybe like this. Okay, if we have not done this measurement, we might just very simplistically assume that the graph will just carry on straight. We would just assume that it obeys Ohm's law, if you remember. V equals to IR, that's Ohm's law. And if we plot the graph of Vi against V using this equation, we would get a straight line because this is a straight line equation. That's Ohm's law. So if we have not measured this, we might think that if all we have measured was the first few points for low voltage, we might think that this is how it looks at higher voltage. So the question now is, now that we have done this measurement, we have taken it out to much higher voltage and we find a curve, let's try to understand why this happens. If we compare those two graphs, okay, let's say if I think of a certain voltage, let's say 50 volts. Let's say 50 volts. Now, according to Ohm's law, if you like, that's what Ohm's law would predict. Right? That's the prediction by Ohm's law. And according to Ohm's law, when the voltage is 50 volts, I would expect that, right, if you go up a straight line to that Ohm's law graph, I would expect that the current would be much bigger than what I actually measured. Maybe somewhere there. Okay, but actually, as I've described, when we do the measurement, we find that the current is a lot smaller. For this voltage. Okay, and one way to explain this, at least a simple step to explain this, is to think that maybe, just maybe, the resistance has increased. Because if you increase the resistance, the current will drop, right? Because there's more resistance to the flow of the charges. So you can think that the current drops because the resistance has increased. So this gives us an explanation, the first step of an explanation, and then we might want to ask, why does the resistance increase? Okay, to answer that question, we can look at the light bulb, if you like, and try to find a reason. Now, if you look at the light bulb, we would try to look for what happens. Is there something else that happened that we can see when you increase the voltage? There is, but if you remember, at very low voltage, there's very little current and there's hardly any light heat. But that as we increase the voltage, we would expect this bulb to start lighting up and warming up. So that's the obvious thing that happens when you increase the voltage. It heats up and lights up. So the temperature increases. So then becomes natural to think of this as a reason. So we could associate the increase in resistance with an increase in temperature. The temperature increases. So in fact, after years of studies by scientists on this topic, we do understand today that when the temperature of a metal is increased, it would cause bigger resistance to the current, and so that the temperature increase is the correct explanation for why the current drops, for why the resistance increases. So we now understand that this graph curves. This graph does not follow a straight line. It curves, or it falls below the Ohm's law prediction because the resistance has increased, and the resistance increased because the temperature increased. So with this understanding, let me now finish up this part by doing a simple calculation by calculating the resistance when the voltage is at 200 volts. Now, I'll just mention that 200 volts is quite close to the 230 volts for the rating of this light bulb. And usually, for the usual operating of a light bulb, if it's just this is the normal filament light bulb. Okay, I should actually write this down as well. We're talking about a filament lamp here. Right, as I said, there are many types of lamps today, like fluorescent lamp, LED lamps, and so on. So I'm just talking about filament lamps that are made by very thin coil of tungsten wire inside that heats up and produces light. Okay, so for this type of filament lamp, if you might have seen one before, it looks yellow, like it glows bright yellow when you switch it on. Okay, and that bright yellow color comes from the filament getting so hot that it glows bright yellow, and that temperature of the glowing filament is typically about 3000 degrees Celsius. Okay, so it's very, very hot. So what I like to do now is to estimate the resistance at this temperature, and I can do that using the points that I measured, because at this 200 volts, I can just take it as roughly close to 230 volts main that I would use this light bulb at. So at this 200 volts, the current that I expect would be roughly 0.2 amperes. And with this knowledge of the currents and the voltage, I can actually use Ohm's law now to find a resistance. If I rearrange Ohm's law, divide both sides by I, then R is equal to V over I. Okay. We then substitute in the values of voltage and current at this point. When the voltage is 200 volts, the current is 0.2 amperes. And we can calculate that. The answer to that is 1000 ohms. 1000 ohms. Now I'm just using very rough values here, but these values are not so far from the actual values in a real light bulb. So what actually happens is that if you recall from my previous calculation, I might as well do it here again. What I found, this is for the resistance here at the high temperature. Now let me also find a resistance here for the lower temperature, for the room temperature. Let me just quickly repeat the previous calculation. So the resistance here is also V over I. That would be 2 over 0.05, 2 over 0.05, and that would be 40 ohms. So you see, from 40 ohms at room temperature, the resistance goes all the way up to 1000 ohms at 200 volts at this 3000 degrees Celsius. So that's the kind of increase in resistance that happens when we switch on a filament lamp, all the way from 40 ohms to 1000 ohms. A huge increase in resistance, and that's quite typical of metals. If you raise the temperature by so much, the resistance will increase a lot.